Welcome to this SE24 OpenMP booth talk. My name is Lutz van der Pas and I work in the Oracle Linux Engineering Organization. In this presentation, I would like to talk about NUMA. I will explain what NUMA is about, how you can find out on your own system whether it has a NUMA architecture and if so, what it looks like, and the kind of support that OpenMP provides to help tuning your application for a NUMA architecture. To start with, what is NUMA? NUMA stands for Non-Uniform Memory Access, and it used to be the realm of very large servers only. Just a handful of systems in the world had a NUMA kind of memory architecture, and for those people using them, they already had to take NUMA into account, but it was still a corner case. That's no longer the situation because NUMA has come down, and you can even find a NUMA architecture down at the processor or socket level. And therefore it has been pretty much become a concern for all of us using OpenMP, because NUMA can impact the performance of your OpenMP application quite a lot. By the way, NUMA in itself has nothing to do with OpenMP, but since we're using OpenMP, we get exposed to it. The tricky and nice thing is that things just work. You need variable A in OpenMP, you will get it. It doesn't matter where it is. The question is, how long does it actually take to get that variable A? That brings the question, how efficiently does your code perform? And I want to talk about the hardware and then move, of course, to the software side of things. But we need to understand the hardware before we can meaningfully talk about NUMA tuning. I will start with showing a node. A node is a computer in itself. It has a bunch of cores for the computational work, it has memory, and it has caches in between. I'm only showing the LLC last level cache here. That's the cache that connects directly to memory. In general, there are more caches than that. But for our purpose, we only need to look at the LLC. Within the cores, you may or may not find what is called hardware threads. It's part of the design. Some cores have it, some don't, and I'll show you how you can check for that to be available. Hardware threads are a way to accelerate the performance of a workload or an application. And they do that as follows. Let's say you're executing your program and there's a gap in the execution. That's actually quite common. Could be a very expensive cache miss. Maybe you're waiting for some I/O. There are all sorts of reasons why the execution flow may be interrupted and the program stops executing for a short while, and you have these gaps. Well, that's kind of a pity because meanwhile the processor is burning energy and you're not making any progress. If you would have two hardware threads, what you can do is use that gap to execute another application. You still need to wait, but why just burn energy in an idle loop instead of running something useful? And that's exactly what hardware threads do. And here in this example of two hardware threads, I can sort of interleave the execution of those two processes or threads. In that way I can save time and I can save energy. That's the purpose of hardware threads. Here I'm showing two cores and they have 4 hardware threads each. Again, that's part of the design. They may or may not be there. In this case they are there and we have 4 per core and the system assigns a number to it. It's called the hardware thread idea. And later on, when I get to the OpenMP support for NUMA tuning, I will return to this topic. Because in OpenMP, if you want, you can control where your software should run down to the hardware thread ID level. It's in general not recommended nor necessary, but the possibility is definitely there. Let's look at a contemporary NUMA system as we see them today. We have the node that I just introduced, but now we have multiple nodes. How do we connect them? We can connect them with a regular network, let's say Ethernet, and then we have a cluster of nodes. But you can also have a customized, highly proprietary interconnect called a cache-coherent interconnect. And that's very different. That's in a way way more sophisticated. It's part of the system design, and what it allows us is to make it, the whole system, a single system image. So while the hardware is distributed, we see there are 4 memory blocks in each of the nodes. There are cores are physically separated. To you won't see that. Thanks to the cache coherence, it will behave like one system You can access, for example, any memory location anywhere in the system, wherever you are. So it behaves like a single system image. That's really nice from a development point of view. Why has this NUMA path been chosen? Well, in the past, you would have a fixed bandwidth that you would share with all your computational elements, like your cores. As you would add cores, that fixed bandwidth would become more and more of a bottleneck. And that's why NUMA was invented. NUMA gives you scalable bandwidth. As you add nodes, you add bandwidth, so it's a much more scalable design in terms of memory performance. In a NUMA system, the memory is physically distributed but logically shared. Again, to you it appears like one memory. You don't see the physical distribution underneath. Shared data is accessible to all threads. You name a variable, you will get it, no matter where it is. You don't know where the data is, and it doesn't matter, you will get it. The only thing is when you start looking at performance, because then it starts to matter where things are. That's what I want to show here. Here I'm showing a system with 4 NUMA nodes. And let's say my thread is executing somewhere in the NUMA node in the upper left corner. If it needs data, that could come from its local memory, as we call it. That's a local access, that's the fastest, that's the best you can do. You can't get any better. But there's nothing that prevents this situation from happening. The data may have to come from relatively far away. It will take time to cross that interconnect and get the data into the core that needs it. That's what we call remote access. Remote access is always slower than local access. How much depends on the system. We're not going to go into that. That's part of the architecture, how much slower and faster is. But for us, what matters is there's local access and there's remote access. And what you don't want is to have too many remote accesses. A couple of them is fine, but it should not be the bulk of your accesses. They should come from the local memory. And I want to show you how you can figure out for your own system whether it has a NUMA architecture, and if so, what it looks like. And there are 2 nice commands that I use all the time myself. The first one is called lscpu. It gives a lot of information, including a block starting with NUMA node. And for each NUMA node, there's a bit of information shown here. We see there are 8 lines. That means there are 8 NUMA nodes. They're numbered 0 to 7. And we see those integer numbers, those 2 columns. What does that mean? The first column shows there are 8 numbers per column, 0 to 7, 8 to 15, 16 to 23, and so forth. What that means is there are 8 cores per node. That's what we learned from that first column. But there are 2 columns. And the second column indicates there are 2 hardware threads per core. If there were 4 hardware threads, you would see 4 columns there. And those numbers are the individual hardware thread ideas. With these numbers, you exactly know where sort of the hardware is. If you pick a number, you can figure out in which node it is and in which core and so forth. Now, again, generally you don't need that fine level of control, but in some cases you want to do it. And with these numbers, you can do so. In addition to the lscpu command, there's another command that I use quite often, NUMA control -H. That will give you a latency table. It's a matrix showing the relative latencies between the nodes. We know that we have 8 nodes. And of course, this is a symmetric matrix. You wouldn't need to show both of them. But we show the full matrix with that command. And the latency from the node to itself is normalized to 10. You might expect 1, but because of Linux scheduling reasons, the latency is normalized to 10. And as we pick a node, let's say node 0, because the situation is very symmetric for all the nodes, we see that the latency from 0 to 0 is 10, but then we see the number 16 for nodes 1, 2, and 3. That means those nodes are further away. Now you can't say it's 1.6 times more expensive. That you can't do that. These are numbers that are used by the scheduler to make scheduling decisions, but it does mean there's a notion of remote access. But what we see as we follow that horizontal line, we see that node 4, 5, 6, and 7 are even further away. They have a higher latency. So what we see, we have 2 levels of NUMA here. Level 1 is the nodes 1, 2, and 3, and level 2 is nodes 4, 5, 6, and 7. That's the kind of information that you learn from the NUMA control command. To summarize, we saw there are 8 NUMA nodes. There are 8 cores per node. Each core has 2 hardware threads, so that means that we have 64 cores and 128 hardware threads in this system, and there are 2 levels of NUMA. I labeled them 16 and 32. It's a fairly complex NUMA system, actually. So here we're looking at a symbolic representation of the matrix that I was just showing. We have a center node. The center node has access to 3 remote nodes. They have a longer access time. And then we have 4 more nodes that have an even longer access time. So again, 2 levels of NUMA in this system. Tuning for a NUMA system means that we want to keep threads and their data close. What you really want to do is whatever data the thread is working on, it should be in its local memory as much as possible. The assumption is the data location is fixed, but a thread may be moved closer to it. We're not going to move data because moving data is very expensive. Packing up a thread and rescheduling it on another node is relatively cheap to do. So it's a lot easier and more efficient to move a thread than the data, and that's what is done in OpenMP. That's handled by the runtime system. And you tell it what to do through the affinity constructs that I will talk about next. The affinity constructs will let you completely control the NUMA behavior of your application. It's a very powerful feature, but you got to get it right. You have to tell the system what to do. And when I say right, I don't talk about correctness. Let that be clear. When you get the right results, NUMA tuning won't change that. The results will still be correct, but the performance could be different. And hopefully you can tweak the settings so that you get better performance. And that brings me to NUMA and data placement. The question is, if it's so important where the data is relative to the threads, where does data get allocated? And there's a policy that controls the placement of the data. There are several policies usually, but the default is called first touch. And it allocates a data page. And we talk about a data page, that's the operating system granularity, how to handle data. It works on data pages. That's a fairly large chunk of data, like 4 kilobyte, 8 kilobyte, 64, maybe 128. It's a large chunk of data. That's what the operating system manages. Those are called pages. And what it will do with first touch, it will allocate the data page in the memory closest to the thread accessing this page for the first time. As suggested by the name, the thread that does something with the data for the first time will own it. And that will determine what we call the home node. Wherever that data is allocated, that's the home node, that's a fixed location. And in that way, you can describe the goal of NUMA tuning is keep threads close to their home node. You really want to achieve that situation as much as possible. As I earlier said, it's unavoidable that you have remote accesses, that's fine, but the bulk of the accesses should be from the home node. First touch is the default on Linux and every other general purpose OS that I know, because it's the right thing to do for a sequential application. When you run your application single-threaded, you want to have all the data in the memory where you're running. So that makes sense. The thing is, in a parallel application, that's not always so obvious. So first touch is a good policy, but in a parallel application, things could be a bit different and not the way you like it. For example, what if a single thread initializes most or all of the data? That means, by virtue of first touch, that all the data ends up in the memory of wherever that thread is running. So a single node has all the data. That means that every other thread not running in that node will have a remote access to get to the data. That will take time. There could also be congestion on the network if there are many threads and a lot of data accesses, but in general, the increase in memory access time is the problem that you're faced with. Luckily, there's very often a surprisingly simple solution how to avoid that situation. Here's an example. I initialize a vector to 0, one thread execute that loop, and that means by virtue of the first touch policy that the data will end up in the memory wherever that thread was running. That's not what we want. The solution is remarkably simple, and actually you can leverage first touch with our loop if we add a parallel for then that loop will execute in parallel with the static schedule. It means that each thread will initialize a slice of that vector. And if those threads are running in the various nodes, then we automatically distribute the data. We let the system do that, and that's a very general principle in NUMA tuning. You use first touch to your advantage. You know that when things are initialized, the location is determined. This is a simple way, but very effective, very common. So you need to look at where the data is initialized and how about the placement at that point. So it starts very, very early in the execution of the program, probably. And that brings me to the OpenMP support for NUMA systems. In OpenMP, it's all about the places. A place is a set, so it can have one or more elements, and those elements define where a thread is allowed to run. You define a place and you tell the system, this is where I would like you to schedule my threads. And then you build a list, the list of places, and that's called the place list. And that place list consists of either symbolic names or a set of numbers. You can mix it. An example of such a symbolic name is cores. That means I want to use all the cores as a scheduling target for my threads. You can go down to the hardware thread ideas that I mentioned in the beginning. And for example, here I have a set 1357. That's a single place. That's in the curly braces. I got 4 numbers, so I have a place with 4 numbers. That means the scheduler has the freedom to choose any location within that single place. Or I could have 4 individual places, and that's defined by the curly braces. And then within a place, there's no choice anymore. When you pick 5, you can only run on 5. In that way, you can give the scheduler more or less freedom in making its decisions. And you do that by setting 2 environment variables. The variable OMP_places defines the place list. It defines where threads may run. OMP procbind defines how threads map onto the OpenMP places. And why would you need that? Well, let's say you have more places than threads. For example, I have defined the place list to be cores, as on the previous slide, and I have 16 cores in my system, and I'm only going to use 4 threads. The question is, which of the cores do you want to use? And that's what you set with the OMP procbind variable. The OMP places, the symbolic names are quite flexible. You can go very low level. You can set it to threads. That means the scheduling unit is a hardware thread, and in principle, all the hardware threads are available for the runtime system to schedule activities on. You could go a little bit higher. You could say cores. All the cores in the system are candidate to run your threads on. Or LL_caches. That's a set of cores that share the last level cache. NUMA domains, a set of cores that share a memory with the same distance to that memory. That's like a NUMA node is, for example, a NUMA domain. Or you could go even higher, a single socket. That's the whole chip in a way. That last one is not very meaningful. I think that gives a lot of flexibility, but you can say, I don't want you to use other sockets in my system, for example, because you can give a number. You can give a number with those names. For example, if you say cores 4, then that means I only want you to use 4 cores. In that way, you can restrict it. As you've seen already, you can define places in terms of the hardware thread ideas. Those could be very long sequences of numbers, and that's why it's very convenient that there's a compacted set notation. The notation is that these numbers are colon separated, the starting value, the total number of values that you want to have, and the increment. For example, if your definition is 0:4:2, that means we start with 0, there are 4 numbers, and the increment is 2, so that expands to the list 0, 2, 4, 6. Here's another example. I define the places to be the NUMA domains in my system. And like in my imaginary system, that will be like the nodes in my system. Or I could say, well, I want to use 4 places and I specifically want you to run on certain hardware thread ideas as shown here. And you have 2 ways of doing it. You can use the individual numbers, but again, that list gets very long. It's easy to make a mistake. So the compact notation is preferred. It's easier to read and less error prone in a way. You can also say, well, I only want to have 1 place, and within that place, I want to give you the freedom. So you can have 4 choices here, and the definition with the compact notation again is preferred because it's easier and shorter. The next step is, now that you have defined your places, is to tell the system how you want to map threads onto places. And again, that comes into the picture when you have more places than threads. So you're going to define the mapping of threads onto the places that you have defined. And you have 5 choices. You can just enable it, leave it up to the system. You can disable it. There may be cases where that's relevant, but in most cases, you'll either set OMP proc bind to primary, close, or spread. Primary means that you want the other threads in the team to be scheduled where the main thread is running, the primary thread is running. Close and spread are defined in terms of the place list. Remember, the place list is a set. These are sets of places. So you can have like 10 places in that list. Close means that you want to use sets that are close to each other in the place list. Spread means you want to spread them out. In a way, what these 2 values mean is that you want to either keep threads very close to each other because you want to share caches, for example, or you want to spread them out because you want to maximize the bandwidth in the system. And here's an example. I set the places to coarse and the binding to spread. That means I want to sort of push out the threads. I don't want to have them grouped. I don't want to have them be close to each other. I want them to be as far away as possible. Now let's revisit that example that I had where I used a parallel initialization of a vector in order to get the distribution. And what we saw was if I had 4 threads, the vector would be spread out over the 4 nodes that I have. The problem is, this is wishful thinking, because how do I know where those threads actually will execute? And most likely, if I wouldn't do anything, the operating system scheduler will keep those threads in a single node, because that's in general better for performance. I need to do a bit more. And now I can, because I have my places and procbind variables. So I can set OMP places to NUMA domains. That means I have 4 places here, the 4 domains, the 4 nodes that I have, and I want them to spread out. That means that when I run 4 threads, they'll each be placed on the individual node. Of course, if I have more threads than NUMA domains, then I'm going to have multiple threads per NUMA domain. But in my example, this is exactly what I want. And I can enforce it by setting these environment variables. A word of warning. It's very easy to make a mistake with these things. It all happens silently and you have no idea, but your performance may not be what you could get out of the system because you may have made a mistake. There are 2 environment variables that I can highly recommend to use. OMP display env is an environment variable that will echo the initial settings. When your program starts, you will see not only the NUMA settings, but you see all the settings. Extremely useful, and you can use it to check your places definition and your proc bind. You can also verify what happens when the program is running, and for that you can set OMP display affinity. It's a programmable interface. By default it has a certain format, but you can change it. And that gives you the dynamic information about the affinity controls, what happens at runtime. I can highly recommend to use these. Well, I hope you found this useful. As always, stay tuned. And remember, if somebody tells you OpenMP does not scale, correct that person and say bad, OpenMP does not scale. Thank you for your time. And before I go, I'd like to point out the following slide with pointers to more information. As always, there's the one-stop place for anything about OpenMP, openmp.org. But there's also a special section with all the material for SE24. So you'll find the videos and all the other material that we have prepared for SE24. So please go there and check it out. And for now, I'm going to say goodbye and wish you good luck in your NUMA tuning and all your other OpenMP activities.